Hello, everyone. We are now starting section 11.6, which has to do with absolute convergence, conditional convergence, ratio test, and root test. And of course, I will explain what all of that means. So before I talk about absolute convergence, we saw in section 11.5, alternating series test, that the sign on our terms can make a big difference on whether a series converges or not. So for example, we had our classic harmonic series diverges. On the other hand, the alternating harmonic series converges by alternating series test. So that sign right there makes a huge difference. In this particular case, it allows this series to converge while this one diverges. On the other hand, let's look at another example. So these two series are the same except for this alternating term. Okay, when I have this alternating term, my series, I could check by alternating series test. This converges. And on the other hand, this series, that's just strictly positive terms, this also converges. We could say it converges by p-test. Okay, so we have two cases now. In this case, this alternating term makes a huge difference, right? This series diverges while this series converges. And in this case, uh, we could take it or leave it. You know, the 1 over n squared converges, and when it's an alternating series, it converges. Now, there is still a difference here. These two series converge, but they don't necessarily converge to the same thing. They would converge to different sums. But as I said when we started maybe 11.3, at this stage, we're not too worried about the sums. We're just worried about whether the series converges or not. So these series both converge. They might converge to something different, but they both converge. So how can we summarize this property that sometimes these negative terms matter and sometimes they don't? That's what absolute convergence is all about. So let's go ahead and define absolute convergence, and then we'll talk more about when these negative terms matter and when they don't. We can define two types of convergence now. So we say a series AN is absolutely convergent if the series absolute value of AN converges, meaning we start with some series, it might have some negative terms. It doesn't have to be an alternating series. Maybe it has only a couple negative terms. But we say this series is absolutely convergent if the series of absolute values converges. On the other hand, if our original series converges, but this series of absolute values diverges, then we say the series AN is conditionally convergent. Conditionally meaning it depends on whether we're including those negative terms or not. So these are we can divide all convergence really into this absolute convergence or conditional convergence. Now, absolute convergence has uh, a nice property that if a series AN is absolutely convergent, then it is convergent. Okay, meaning if the absolute values converge, then my original series will converge as well. So let's see an example of that. Actually, we can go back to one of our previous examples here. This example here. So if I ignored, let's see, this second series is the series of absolute values of these terms, right? If I said, AN was these alternating terms 1 over n squared. Okay. Then this would be my sum, my series an, right? And then this series would be absolute value of an. So I see here that my series of absolute values, we said it converges by p-test. So I don't even have to check that this converges by alternating series test. Since these absolute values converge, I know that this series has to converge as well. So that's the power of absolute convergence. It tells us a lot about the convergence of our original series. So I can check this and I get a lot of information about this. Okay. So let's develop a little intuition on why this works. Why can why does absolute convergence imply convergence? So this result, absolute convergence implying convergence, it'll follow easily if we can show this type of inequality. If we have, let's say, for a series an. So this series an, maybe it has some negative terms, maybe some terms are, maybe it's alternating series, or maybe just a couple terms are negative. But we want to show that this sum is always going to be less than or equal to the sum of the absolute values. And on the other hand, we want to show the sum of our original series is greater than or equal to the negative of the series of absolute values. So this is the inequality we want to show, and we can do this in a couple steps. First, we can show it for just two numbers. So let's say a1 and a2 are real numbers, which we can write with this notation here. This means a1 and a2 are in the set of real numbers, okay? So a1 and a2 could be positive, they could be negative, they could be fractions or integers or decimal numbers, anything, it doesn't matter. We have something called the triangle inequality. Okay, so a1 plus a2, the absolute value of a1 plus a2, that's going to be smaller, less than or equal to when I split up the absolute values. You can try this on your own. Think about, let's say, a1 is equal to 5 and a2 is equal to -3. And then this holds for, but it holds for all real numbers. And on the other hand, we can see that this absolute value of a1 plus a2, that should be greater than or equal to a1 plus a2. Okay. So what's important is that this is less than or equal to this. Okay. And then on the other hand, let's see, I could say a1 plus a2 is greater than or equal to the negative of this, which is greater than or equal to this. So what do I have? How can I condense all this into one nice inequality? I could say this. Oh, and actually I already see a mistake. This should be a minus sign. All right, so it holds for two numbers. And in fact, it holds for any finite amount of numbers. So if I have a1 through a k, it holds. Just by, we can, if you wanted to know why this works for k amount of numbers, let's pretend a1 plus a k minus 1 is a single number. If I add all those together, I'll get a single number. So I should have, actually, instead of writing it like this, I'll do it like this. So my first step could be writing something like this. I pretend a1 to a k minus 1 is a single number. Then I got ak over here by itself. And then I could write the inequality like this, considering this as a single number, and then this is split off by itself. And on the other side, I have a similar inequality. And then in the next step, I could say, I could repeat the process. I could say, okay, well, a1 to a k minus 2 plus a k minus 1. That should be less than or equal to this term and greater than or equal to this term. So this is just about a, let's see, this term here. We can say that this term is less than or equal to this and greater than or equal to that. And I combine these two inequalities and a lot of similar inequalities, and I get a1 plus dot 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 ak is less than or equal to all the absolute values added up. And greater than or equal to the negative of all the absolute values. This is a process that's called induction. That's very common to use in mathematics. How could we write this in summation notation? We could write it like this. So the sum from 1 to k of an is less than or equal to the sum of the absolute values, and it's greater than or equal to the negative of the sum of the absolute values. Okay, and once we have this line, maybe it's obvious that we can extend this to infinity and write this. So my series with possibly negative terms is less than or equal to my series of absolute values, and it's greater than or equal to the negative of this absolute value series. Okay, and this is really all we need to show the at least intuitively, the theorem, that the result that absolute convergence implies convergence. Okay, meaning if the series of absolute values converge, then my original series has to converge. Why? How can I remember how I can write that a series converges? We can say it's less than infinity, right? Or we could just say, if let's say if the series of absolute values converge, it converges to some number. We can say this series equals C. Okay. So let's say this series converges and equals C, then we have to have, for my original series, since this is equal to C, we have to have my original series is less than or equal to C and greater than or equal to negative C, where C is a finite number, right? So that means my series here in the middle has to converge. It can't go up to infinity. It can't go down to negative infinity. It has to converge. On the other hand, what happens if this series of absolute values is not convergent? What if it's divergent? Okay, so if, let's see, I always have this inequality, but if my series of absolute values is divergent, meaning it goes to infinity, then all I know is that my original series is somewhere between infinity and negative infinity, meaning this series could be anything. It could be convergent to some finite value, it could diverge to positive infinity, it can diverge to negative infinity. So we know nothing about our original series. Okay, I'm back after an internet mishap. So as I was just saying, we have our original series. Okay, if that series of absolute values is divergent, all we can say is that this series is less than or equal to infinity, greater than or equal to negative infinity. So this series could be anything. It could be convergent, it could be divergent. Uh, we really need to check further. We need to do more work on this. We can't just rely on information from the absolute values. We need more work. Okay. So we can summarize the previous work with this theorem. If the series AN is absolutely convergent, then it is convergent. And that might sound redundant, but what is this saying? This is saying if the series of absolute values is convergent, then our original series is convergent. So the way I think about this is I see this word absolutely and absolutely convergent. That refers to absolute values, right? We're talking about whether or not this series is convergent. So on that hand, it means absolute values. But how I think of this is absolutely as a synonym for definitely. Okay, if the series AN is absolutely convergent, then I think to myself, it's definitely convergent. It doesn't matter if some of these terms in here are negative, if they're all positive, no matter what's going on, whether I have an alternating series with my entries or all my terms are positive, this series is definitely converging. So absolutely convergent, you can think of it as this series is definitely diverging. Now, what does this theorem not say? If the series is not absolutely convergent, okay, if the series is not absolutely convergent, that doesn't necessarily mean the series is divergent, right? So this might sound confusing, but let's write this out. So just because the series of absolute value is divergent, that doesn't necessarily mean this series, my original series, is divergent. So let's see what we have. If this series of absolute values diverge, we can still have the original converging. Okay, it could be conditionally convergent. Okay, so the example I would give would be the alternating harmonic series. If my ANs are these alternating terms, these signs with alternating, these terms with alternating positive, negative signs, we've seen that this series converges. But if I look at my series of absolute values, I just have the harmonic series that diverges. So my series of absolute values diverges, my original converges. So it is conditionally convergent. So the next question is, how do we tell if a series is absolutely convergent or not? There's a couple ways to do this. The first way I would say is the direct approach. This is what I call it. It's not official terminology or anything. So I want to figure out if this series, AN from 1 to infinity, is absolutely convergent. So there's a fairly straightforward way to do that. I want to check if this is absolutely convergent. I just look at the series of absolute values and use the tests I already know to see if this thing's convergent. I could use tests like p-test, integral test, what else do I have? Geometric series test, things like that. So there's a lot of stuff I could apply to this series of absolute values. Okay, so I'm going to just check this thing directly and see if this is convergent. If this is convergent, then I say my original series is absolutely convergent. There's two other ways I can check to see if this series is absolutely convergent. And those are ratio test and root test. And we're going to use these these tests a lot in the following sections as well. So we got to get a good handle on these. So let's start with the ratio test. So the ratio test states this. Let's assume I have this series AN. Again, some of these terms might be negative. Maybe it's an alternating series. It doesn't have to be an alternating series. Maybe just a handful of them are negative. If I take the absolute value of AN plus 1 over AN, so I'm looking at two consecutive terms, and I take that limit as n goes to infinity. if that limit gives me a finite number, L, and that L is less than 1, strictly less than 1, then my series is going to be absolutely convergent, meaning this series will be convergent, which implies my original series is convergent as well. They would both be convergent. On the other hand, if that limit is greater than 1, or if the limit is equal to infinity, then both of these series are going to be divergent. So notice that 1 and 2 apply, these conditions apply to both series, okay? So if the limit is less than 1, the absolute value series is going to be convergent, which means my original is going to be convergent as well. On the other hand, if the limit's greater than 1, that means my original series is going to be divergent, and that means my absolute value series is going to be divergent as well. And then condition 3, if the limit is equal to exactly 1, we don't know what's going on. The test is inconclusive. We have to do something else. So ratio test is where you're going to start to see a lot more of the factorials. I have made a video on factorials already. If you need a little help on the algebra factorials, we got to be able to simplify factorials. You may want to take a few minutes to watch that now. It's only like 8 minutes long, I think. So let's look at this series. -1 to the power n, and let's say we have 2n over n factorial. And I want to see, is this series absolutely convergent, conditionally convergent, or divergent? And a little tip that whenever you see factorial, try and use the ratio test first, okay? Ratio test works really well with factorials. So with that in mind, let's try a ratio test on this. So first, let's figure out what is an plus 1 over an with the absolute value bars. What does this look like? Let's write out this term first. Well, an plus 1, I'm just going to replace all my n's with n plus 1's. And I'm talking about absolute values, so I can ignore any negatives. So this would be my an plus 1, 2 times n plus 1 over n plus 1 factorial. And then an, absolute value, that would just be my original numerical term. That would just be this. Okay, so an plus 1 over an, I'm going to divide this by this, which is the same as multiplying by the reciprocal. And now let's try and simplify this. How can we simplify this? Well, first of all, let's rearrange this a little bit. Let's get the factorials over the factorials and everything else over everything else. I'd have this. Now, can I simplify this at all? So here's where it might help to have watched the factorial video. How can I simplify this factorial term? Let's rewrite what we had. Oh, let's see, I should have n factorial on top. Okay. If you guys have watched the factorial video, you'll know that this n factorial over n plus 1 factorial, that simplifies as 1 over n plus 1. Okay, and then this, I'll expand this expression. This would be 2n plus 2 over 2n. Okay, so this is my simplified version of an plus 1 over an. And now I want to take the limit of this thing. I want to take the limit of an plus 1 over an. Okay, so maybe it's hard to see right away what this is, but consider it piece by piece. What's the limit of this term here, 1 over n plus 1? Well, that limit goes to 0. And what about this term here? 2n plus 2 over 2n. Well, let's see. I got same power of n on top and bottom. So the limit should be the coefficients on the ends, 2 over 2. So this limit is 1. So the limit of these multiplied together should be 1 times 0. So 0. Okay. And what does my ratio test tell me? Okay, this would be condition 1. If a limit of an plus 1 over an equals L less than 1, my series is absolutely convergent. So I saw my limit is 0. That's less than 1. So my series is going to be absolutely convergent. So I conclude that this series is absolutely convergent. And again, whenever I use a test, I want to say what test. So I would say by ratio test. Okay, let's go ahead and move on to the root test. The root test is extremely similar, at least in our limits. I'll explain what I mean. So for the root test, again, we're starting with some series an that could have some negative terms. And then instead of taking the ratio of an plus 1 over an, what are we doing? We first take the absolute value of our term an, and then we take the nth root of it, and then we take the limit as n goes to infinity. Now, if that limit exists and it's equal to some number L, which is less than 1, then the series is going to be absolutely convergent. Okay, so just like with the ratio test, if the limit's less than 1, our original series is absolutely convergent. And just like the ratio test, if the limit of this nth root of absolute value of an, if that limit is greater than 1 or infinity, my series is going to be divergent. And again, if the limit is equal to 1, the test is inconclusive. So we see very similar conditions. Once again, if we have the limits less than 1, then the series is absolutely convergent, meaning this series of absolute values is convergent, which implies my original series is convergent as well. On the other hand, if the limit's greater than 1, then both of these are going to be divergent. And if the limit's equal to 1, we don't know. We have to do something else. So when do we use root test? We use root test when we see this isn't the only case, but when I think to use root test is when I have everything to the power of n. So an example that's in the book. So let's say I have, and I'll modify it a little bit. Maybe I have, I'll throw in a negative sign there. Okay. So maybe I have 2n plus 3 times negative 1 over 3n plus 2, all to the power n. So this would be an alternating series. And we want to figure out, is it absolutely convergent, conditionally convergent, or divergent? So since I see everything to the power n, let's try root test. That's my clue. I want to use root test. So first of all, let's figure out what an is. Well, if I take the absolute value of my an's, that's just going to be the same thing I have in my series here, but I'm going to drop the negative. Okay, so that's my an. And now what does my nth root of an look like? Well, I'm going to take the nth root of this, but I'll go ahead and write it out. My nth root and my power n should cancel, right? Remember that nth root is the same as something to the power of 1 over n. So this is the same as power n to the power 1 over n. When I take when I have one exponent raised to another exponent, I multiply the exponents together. So what's n times 1 over n? That's 1. So this is my nth root of an right here. Okay, so this is equal to this. What's my next step? I want to take the limit of that. So what is this limit here? 2n plus 3 over 3n plus 2. Again, since I have same power of n on top and bottom, I look at the coefficients. That limit is equal to 2/3. So what does my root test tell me? Okay, my limit's equal to 2/3, which is less than 1. So my series should be absolutely convergent. Again, my series is absolutely convergent. And I would say by root test. Okay, I've shown something that was absolutely convergent. Divergent is very similar. I do the same process, and if my limit's greater than 1, my series is divergent. What about conditionally convergent? The ratio test and the root test. Uh, let's see. Let's look at the root test for a second. The root test, none of these three conditions say anything about conditionally convergent, right? And same thing with the ratio test. If I look at the ratio test, none of these three possibilities say anything about conditionally convergent. So how can I show something's conditionally convergent? Okay, we should we should never say we should never say an is conditionally convergent by ratio test or root test, because these tests, we don't use these tests to show conditional convergence. First of all, when do I try and show conditional convergence? Maybe I try the ratio test and I try the root test and I get my limit is equal to 1. So that's that inconclusive case. So maybe that's a hint that something weird's going on. So maybe my series is going to be conditionally convergent. For example, uh, if I had tried to do the alternating harmonic series, if I had tried to test this for um, absolute convergence and I used the ratio test, I would get my limit is equal to 1. Okay, so that's that inconclusive case. So maybe that's a hint that I should see if this is conditionally convergent. How do I show something's conditionally convergent? I have to do two things. First, I have to show that the series of absolute values is divergent. Okay. And I can't use ratio test or root test to show this because I want to show that this is divergent. But I also, step 2 will be showing that my original series is convergent. Okay. So if I use ratio test or root test to show that this is divergent, it's also going to show that this is divergent. Okay, so that's not what I want in step 2. So I want to show this is divergent using something besides ratio test or root test. I want to use something like maybe the divergence test. Probably not divergence test, but something similar, maybe like integral test, p-test, okay, or geometric series test, something like that, some previous test I know that tells me about divergence, but not ratio test, not root test, okay? So I want to show this is divergent. And then step 2 would be to show that my original series is convergent. And again, I don't want to use ratio test or root test for this. I want to use maybe alternating series test, something like that, something that will allow me to keep my negative terms and show that this series is convergent. Usually it's going to be alternating series test. Okay. So if I want to show something's conditionally convergent, I need to show these two things. I need to show the series of absolute values is divergent using that direct approach I talked about earlier, which is my terminology. Okay. So not using ratio test, root test, and then I need to show this series is convergent. Okay. And if I showed these two things, that's the exact definition of conditional convergence, right? We said conditional convergence is when the original is convergent, but the series of absolute values is divergent. So really, it's just by the definition of conditional convergence. Okay. So I know I maybe went over this. Maybe I didn't do enough examples for you guys, but I will put out a problems video uh, probably tomorrow. That'll go over a lot more of these problems and you'll see how they're worked. Hopefully you guys got the theory down or will on rewatching. Let me know if you have any questions.